we'd like to give a special welcome to Andrew Briggs, Professor Andrew Briggs, for our next talk. Andrew is actually the only one of our speakers who has something very special about him, and that is that he's the only one to have flown his own plane from Oxford to Cambridge to be here. So I think that's an impressive part of the CV, and lands just near Cambridge in Bourne Clinic. I always think of Bourne Clinic and in vitro fertilization when I think of Bourne, but apparently there's also actually a landing place there as well with a control tower and so forth, which I have only just been learning about. So fascinating little bit of information there.
Have you learned to fly in Chris Action's flight simulator?
Yeah, we discussed that.
Yes, I think there could be room for collaboration here, which unexpected collaborations grow up through these courses. So Andrew has actually had long connections with both Cambridge and with Oxford. In fact, he studied for a degree in physics at Oxford, and then he came over here to Cambridge to do a PhD, and also stayed on to do another degree here in Cambridge, this time in theology. So he really has a very, very strong background in both science and in theology. He then went back to Oxford, where he's now the Professor of Nanomaterials and also Director of the Quantum Information Processing Interdisciplinary Research Centre, which is a whole collaboration throughout the UK and beyond, I think, on this particular topic. And his recent work has demonstrated some very precise manipulation of quantum states, and has actually contributed to the entry of the smallest test tube in the Guinness Book of Records. So some practical outcomes of nanotechnology. He's also a professorial fellow at Science College. And I would just like to again thank him in particular for being a member of our editorial board this time of the journal Science and Christian Belief, which is a journal which I edit. I hope you got a free copy in your handouts, in your packs and whatever. No, you didn't. Oh, you did? You did? Good. Most people did. Anyway, if you didn't, make sure you see. The speakers didn't. Okay. Hopefully everyone got a free copy, a complimentary copy. And Andrew is on our editorial board and has been for many years, so we want to thank him for that. And so he's going to talk to us about the whole area of quantum theory and information becoming physical. Thank you very much.
Well, thank you, Dennis. After that generous introduction, I feel I can scarcely wait to hear myself speak. You'll find a handout in your packs, even if you haven't got the special issue of Science and Christian Belief. Because this is an interactive time together, I've adjusted some of the slides in the light of points that have already come up, so you'll find they don't exactly follow what's here. And because it should be interactive, don't wait till the end to ask questions and make points for discussion. Do please chip in. You may know the story of the professor from Oxford who was giving a sort of general science talk at the local psychiatric hospital at Littlemore. And there was someone sitting in the front row, just about there, who sat there saying, "Rubbish, rubbish, rubbish, rubbish." And after a bit, the professor turned to the consultant who'd invited him and said, "I'm sorry, this is terribly distracting. I can't carry on with that going on the whole time." And the consultant said, "Oh, please do. We've been having terrible problems with this patient, and now at last he's talking sense." Here is the cover of the Guinness Book of World Records 2006. And if you have bought it as a Christmas present for your nephew or niece or someone like that, and you turn to the entry for the smallest test tube, you'll find this experiment here. And this is a single-walled carbon nanotube. And I want you to get some idea of the size of this. If we took 50 of them and laid them side by side, and then we took 1,000 of those bundles and laid those side by side, we'd end up with something the diameter of one of the hairs on my head. It's 1.4 nanometers in diameter, and inside it we've placed these little molecules here, which consist of 60 carbon atoms. An ordinary football has 20 white hexagonal patches sewn together with 12 black pentagonal patches. And if you take the vertices where the three seams meet, there are 60 of those on a football. If you were to place one carbon atom at each of those 60 vertices, and then shrink that 100 times, and then shrink that 1,000 times, and then shrink that 1,000 times again, you'd end up with one of these molecules of 60 carbon atoms, also made up of 20 hexagons and 12 pentagons. And there are actually 3 of these C60 molecules here, and there's one oxygen atom there and one oxygen atom there, and then there's also an oxygen atom between those two. Where there's an oxygen atom, they react chemically and bond together. We're looking at these in a high-resolution transmission electron microscope. Under the influence of the electron beam, the C60 molecules move in the nanotube. And you can see that the 3 move and come together with the 2, and they kiss each other. But it's a van der Waals kiss, not a covalent one. And so as the experiment goes on, those are at 5-second intervals, they can move apart again. So the Guinness Book of Records thought of this as the world's smallest test tube. The volume of the test tube that you're seeing in those pictures is about 20 yoctoliters. A yoctoliter, you will recall, is 1,000th of a zeptoliter, and the number of yoctoliters in a teaspoonful is about equal to the number of teaspoons full in all the world's oceans. The work was published on it was the cover story of the first issue of the 40th anniversary year of chemical communications. They kept it back for that. By the time it appeared there, lots of other people had read about it, and we were most pleased that the Iranians should be so well informed. It got half a page on page 4 of the Iran Daily News. The way of putting these C60 molecules into the nanotubes made the cover story of another journal, and it's done by putting them in supercritical carbon dioxide in this little machine here. And that enables you to put them in at temperatures pretty close to room temperature, which is useful if they're functionalized. Now, people have made theoretical predictions about how these C60 molecules would pack inside nanotubes. For example, if you change the diameter of the nanotube, a couple called Hodak and Girifalco produced this theoretical model that showed that if you've got a rather small diameter nanotube, you just get a row of them, and then as you increase the diameter of the nanotube, so the packing should change into these different phases. And Andrei Klobostov got a series of these and looked at them in the electron microscope and was actually able to find the different phases that have been predicted theoretically, at least 3 of them in that slide there. You can put atoms inside these cages of carbon atoms. They're called fullerenes because the people who discovered them thought they looked like the geodesic domes created by the architect Buckminster Fuller. So we can put atoms inside the fullerene cages, and then you can put those inside a nanotube, and you can see that you've done it. So here's what you would see if you looked over Andrei's shoulder in the electron microscope. Here's a single-walled carbon nanotube. This one's also about 1.4 nanometers in diameter. And these are cages of, in this case, 82 carbon atoms. And then inside each one of those, there's one cerium atom. You can see that as a dark spot. And you can see that from one frame to the next, they move a little bit under the excitation of the electron beam. And you can even study the orientation and do statistics of the orientation by looking at it, by measuring them and plotting them. And this is a remarkable thing that's one of the characteristics of nanotechnology, which is that we can manipulate individual molecules and atoms. Well, people have been doing that for a long time. I mean, cooks have been doing it for centuries, if not millennia. But we can do it with individual molecules and atoms.
Could I interrupt? You said
yeah.
cook, and I think it's to be clear what the picture actually is. You've got an electron beam coming in from one side.
Yeah.
It's scattered by the, passes straight through the material.
Yep.
And that's just sort of a photographic plate essentially from the
Yep.
other side.
Yep.
Is that?
Yeah, it's a digital camera in fact. Yeah. And you can imagine when you're sitting at the microscope, you adjust the focal conditions, and you're probably seeing contrast mainly from the changes in phase.
What are the electrons scattering off?
Well, they're scattering off the charges around the atoms. So it's
So
the,
they're
it's the
polarised.
charge cloud around the
So
carbon
they
atoms.
polarize it.
Pardon?
So they polarize the outer shells. They have this.
I doubt they polarize it much. No, I doubt they do that because it's pretty conducting by the standards of beam current that we're using. But the electrons probably undergo a phase shift as they go through. And then if you adjust the apertures and the defocus correctly, or the focal series, then you get nice contrast like you see in that picture.
How long do these things last?
Pardon?
How long do these nanotubes
Depends on the voltage that you do it at. The threshold for these materials is about 84 kiloelectron volts. So a lot of electron microscopes work at about 100 kilovolts or more, and then you don't get very long to look at them. But if you pull it down below about 80 kilovolts, then you can go on looking at them for hours without degradation. So one of the things about nanotechnology is that you can manipulate these things and see what you're doing with the kinds of microscopes that have atomic resolution, of which the transmission electron microscope is one. The other thing that is new about nanotechnology is that as we make these structures smaller, so discrete quantum states emerge, and you can study them, and you may be able to exploit them technologically too. And that's already happening in biological labeling, because if you make these little colloidal quantum dots, they have discrete energy levels, and that means they have sharp spectral lines, and you can use that for labeling and finding out what's going on in biological experiments. But as I hope we'll see as we go on, the quantum world offers you much more than simply discrete quantum states, and that's where a lot of the fun is. Now, I've said that you can put things inside these molecules, and there's actually quite a lot of different things you can put inside. The ones I've just been showing you are ones where you take 82 carbon atoms and you put inside one metal atom. And you can put in most of the lanthanide series and quite a lot of others like scandium and so on as well. You can create molecules which are rather like an ammonia molecule in that they have nitrogen at the center, but instead of having hydrogen around, they can have metals around. Erbium is one that we study a lot, and scandium we do. You can mix and match actually. And if you create those in your arc discharge chamber, then you can get a cage forming around, in this case, of 80 carbon atoms. 80 carbon atoms by themselves would not be stable, so you can't have a C80 cage by itself, but this acts as a template which stabilizes the 80 carbon atoms, and you can get it then. And the most miraculous molecule of all that we love in the lab is this one here. This has got 60 carbon atoms, and it's got one nitrogen atom inside it. And the miracle is that, and I'm using the term loosely, that the nitrogen atom doesn't bond with the carbon, which is what I think anybody would have expected before this had been discovered. And the nitrogen atom sits inside it like an isolated nitrogen atom, scarcely altered actually from what it would be if it was a nitrogen atom all by itself in space. And that means that you can do atomic physics experiments in a solid state structure. And what I want to show you now is some of the ways that one...
About the thermal fluctuations.
Pardon?
What temperatures is going on? The thermal fluctuations.
Well, it works perfectly well at room temperature. The experiments I'm about to show you were done at 4 Kelvin. There are thermal fluctuations. One of the things that we've shown is that and I'm going to get technical just to show this questioner that I know what I'm talking about, and the rest of you is the question is, we've talked today quite a bit about quantum decoherence and what's the mechanism of coherence. And people used to think it was the thermal fluctuations of the cage banging against the nitrogen atom. What we've shown is that it's an Auerbach process, which involves two photons, and therefore it's more subtle than what previously people had thought. Now back to what the rest of you can follow. And what I want to show you now is how we can take a spin on one of these nitrogen atoms, and we can do wonderful experiments with it. And in a moment I'll talk you through this slide, but I'm going to start off illustrating things from a globe. So here's a globe. It's always difficult to know what orientation to present the globe. So granted that we've got friends here from sort of the Mediterranean and so on, this is quite good. When I've got friends from India and Japan, I like this orientation here. It causes immense distress to my friends from America, who can't understand how you could ever present a globe without America at the center of it. So for my friends here from Canada and so on, there you are. I hope that makes you feel comfortable. You probably know the absolutely disastrous questionnaire that was put on the web asking people for their opinion on the solution to the shortage of sufficient food in the rest of the world. And I mean, this was a more misunderstood question than you can imagine. The people in Africa who saw it scarcely knew what sufficient food was. The people in Europe who saw it scarcely knew what shortage was. The people in the Middle East who saw it scarcely knew what solution was. People in China who saw it scarcely knew what opinion was. And the people in America who saw it scarcely knew what the rest of the world was. What I want you to imagine is that spin up is represented by the north pole of this globe, and spin down is represented by the south pole. And we've said time and again today that one of the wonderful things about quantum states is that you can have a superposition of different states, so that a spin can be both spin up and spin down at the same time. And the key point about representing it on a globe is that this being both spin up and spin down at the same time is not represented by a point on the axis of the globe. It's represented by a point on the surface of the globe. And therefore this superposition state needs, in order to represent it, both latitude and longitude. So suppose
This is spin and a half system?
let's call it spin a half,
Yeah.
all right? And
There's two states.
if you'll allow me as an approximation, I'll talk about this as a spin a half system. It isn't, but we do the experiment in such a way that it's indistinguishable from a spin a half system. So it can be up there, so that's ms is plus a half if you're thinking in those terms, and down here there is ms is minus a half. But when we have the superposition state, there's a quantum phase between those two. There's also a global phase that we throw away, we're not interested in. And what that means is that if you had something that was a superposition of equal amounts of spin up and spin down, it would be represented as a place on the equator, but Nairobi is not the same as Singapore, and the phase matters. Now, in the pictures that I've got here, this sphere, for these, the technical term for it is a block sphere, but you can think of it as being just like that globe there. And the particular experiment we're doing that's represented here is what's called a bang-bang control on the nuclear spin of the nitrogen atom that's in this C60 cage that I was showing you. And the nitrogen atom has got both nuclear spin and electron spin, and for present purposes, please think of them just as spin a half each that can be up or down. And I've represented them here with the first digit describing the nuclear spin and the second digit describing the electron spin. And we've put on a magnetic field so that it introduces some splitting of the energies. This is not to scale because the electron spin energies get split by about 3 orders of magnitude more than the nuclear spin energies. And we talked a bit today about decoherence, and the purpose of these experiments is that they're a way of helping the nuclear spin to remember where it was on the Bloch sphere, even when there's quite a lot of decoherence junk coming in from the outside world. And in fact, to make the experiment work more dramatically, some radio frequency was introduced that would keep changing the nuclear spin between that state and that state. So you can think of that as constantly moving it around the belly of the Bloch sphere, or if you like, in terms of the globe. Sorry, Becky, to make your life so hard, moving around there on the globe. And now what you do is this. Supposing this excitation from outside that we don't want is making it move around there. When you get to that point of the globe, you go bang, and you hit it with some radiation, some microwave frequency that will excite the electron spin. And so it sort of picks it up here and brings it back down there. And one of the things that you'll see later, I'll show you a bit of maths that has a -1 sign in it. That has the effect of picking it up off the Bloch sphere and putting it down there with a minus sign. And then, under the influence of the RF, it carries on round. You hit bang again, and it goes up and comes back down. And that's the equivalent of picking it up and putting it back there. Now, everything I've shown you up till now has just been sort of diagrams, and anybody can draw diagrams. And the key point that I want you to get from this slide is that you can do this experiment. It actually corresponds to an experiment that you can do in the lab. And here are the data. The black curve here is a measurement of the nuclear spin going round and round on the Bloch sphere if we don't have the bang-bang control. And to be specific, this axis along here is time, that's 400 microseconds. And this axis here is the latitude on my globe of the nuclear spin. If you want to be posh, you can call it an SZ measurement. Now we do the experiment with the bang-bang control. So we come round here, hit it with a bang, and it goes at very high speed back to there, and then it carries on round. And you can see there's the bang, and now it's carrying on round. And now another bang, and it's carrying on round. And now another bang, and it's carrying on round. That might look like bang control. Why do I call it bang-bang control? Well, it's a term that comes from electrical engineering, and is a classical technique. But it does something rather clever for us, because it might be that I don't get the excitation quite right. And one of the pathologies, if I don't get the excitation quite right, is that it comes round here, and I do a bang, and instead of it going 180 degrees round the equator, it might only go, what should we say, 170 degrees round the equator. So that's not quite right. So then it goes round this circle here, which is no longer a great circle on the globe. And now if I hit it with a bang that has a systematic error in it, so again it's got 170 degrees instead of 180 degrees, you can see that it does achieve what we wanted. So the bang-bang is much more effective than the bang, at least it's more immune to errors. And the little animation that you had on the beginning just shows you that's the bang, and that's the second bang. And there's the first bang, and the second bang. So, I mean, at this point we've got a choice. You know, either we can just sit watching that for the rest of the evening, or we can carry on. I don't know if you want to vote on that. The trouble is you might prefer just to sit watching that. You know? A bit like watching the washing.
Did you do it in indoor? How did you do it?
Yeah, it's an indoor experiment. And in fact, the measurement of the Z projection of the nuclear spin is done by an indoor measurement, which turns out to be easier and more sensitive than a conventional NMR experiment. So in fact, I cheated a bit because this experiment is what you do after you've sort of tuned the thing up and you've minimized that systematic error. But you can now develop the technique, and instead of doing bang, 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 you can do bang, 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 bang. And if you do that, you can hold it, you can lock it on to some value, and then if you want to, you can switch that off, and then switch it on again, and hold it at some new value. And so you can keep playing around with this. And the key point that I want you to get is that these are theoretical concepts in quantum theory that we can make work in the experimental laboratory. Now there's one more concept that I want to cover before I get on to the significance of that, and that is the concept of entanglement. When I say cover, that's a stupid thing to say. Touch on. We've talked a bit about entanglement already. Rather than labouring the mathematics, let me invite you to participate in a little experiment with me. And the experiment is this. If you look at those wire frames on the screen, how many different ways can you visualize that as 4 cubes? Who's going to be brave and have a shot at answering that question? 16. How many can you visualize?
Just 2. They're all locked together.
Yes, all right. Most people can't. I mean, those who say 16, are you saying that because you think, well, it's 2 to the power of 4? Or are you saying because you can actually see the first one and the second one from the top, and the third one and the fourth one from the bottom?
It's locked.
So most people can see them like that, as from above. All right. And most people can see them like that, as from below. But as Chris was saying, it's very difficult for most people to see any other combination of them, to visualize it. And so, I don't want to overplay it, but if you like, that's a little sort of metaphor of superposition, because you can look at them from above or below, and entanglement, because to most people they all look the same. And it's actually a sort of animation of the Schrödinger cat experiment, where all the molecules in the cat are in an entangled state that corresponds to it being alive, or all in a state where it corresponds to it being dead. And incidentally, one of the reasons why it's so difficult to do Schrödinger cat-type experiments in practice, and certainly on a real cat, is that the coherence time of the states is far shorter from the time that it would take you to work out whether the cat's alive or dead, you know, the time of a heartbeat or a cat breathing or something. I think that's also why, it's the basis of the skepticism that was being expressed earlier for quantum entanglement to be playing a significant role in the human brain. Coherence time, I should just give you some terminology. So let's just go back to a single quantum state. The lifetime of the state is how long it remembers what its latitude ought to be. So if it's a superposition state here, how long does it remember that it's superposition rather than going to the North Pole or to the South Pole? In spin resonance jargon, that's often called T1. And the coherence time is how long it remembers what its longitude ought to be. Is it at Ecuador or Nairobi or Singapore? And in spin resonance jargon, that's often called T2. Now, these concepts of entanglement can also be demonstrated in the laboratory. Let me give you an experiment that was done a couple of years ago in Oxford. It was done in an ion trap. This is just to remind you that it's a real laboratory. There's a vacuum chamber here that has a vacuum in it that's rather better than any vacuum you get between here and the moon. And inside, this spot here is pointing to some ions, some calcium ions, that are arranged in a line. And here are the calcium ions, you can see them inside. It's quite an interesting problem in classical electromagnetism as to how you can support ions electrostatically like that, because dear old Maxwell, to whom we're also grateful, showed that the best you can do is to make a potential that looks like a saddle. And so if you try to put the ions at the point on the potential that looks like a saddle, although they won't go up the hill that way, they'll fall down the hill that way. So you now have to make something that's like a saddle on a rotating record player, turntable. And if you do that suitably, then you can keep the thing in the middle of it, and that's how the experiments are done. And you can make measurements on the states of individual ions in the trap. And here are some oscillations like the ones that I showed you for the nucleus of the nitrogen atoms. In the trade, they're often called Rabi oscillations. But you can also, with this experiment, demonstrate entanglement between two ions. And the easiest way to analyze and present the data is in terms of the density matrix that was referred to earlier this afternoon. And if you're getting nice entanglement, then these elements of the density matrix on these corners here are nice and big. And you can see how well they've done in this particular experiment. They've achieved 83% fidelity in this entangled state. So these are real experiments that you can really do in the laboratory and watch them. Just as a little excursus from my main point, I suppose that one can say that the maths of this was worked out in the 1920s, and in the 1930s, particularly the early 1930s, by then it had become the subject of great philosophical debate. What does it mean? And we've talked already today about some of the key players in that debate. It took 40 years to get from it being a philosophical debate to it being the subject of experiments. And the experiments were by and large done in the 1970s, the first ones, using, yes, advances in laboratory techniques and equipment, and also advances in the mathematical analysis that had come in the 1960s. If the sort of thing that we're working on now works out and is successful, after about another 40-year interval, in other words, by the 2010s, what was the subject of a philosophical debate became tested in experiments will become the basis of technologies. And at each stage in that process, you have to think afresh about what the meaning is of these things. And one of the things about the Bell inequalities is this. Supposing we're doing one of these experiments where we have, well, it's the two houses that Gerard was telling us about, and we're looking at the windows, and he said, you know, you could look at window 1 here and window 1 there, but not window 1 here and window 3 there, or however he presented it. Supposing that you're looking at window number 1, or you tell each other, we're going to look at window number 1, okay? And then this guy, at the last minute, changes his mind. He says, I'm not going to look at window number 1, I'm going to look at window number 2 instead. And he does it so much at the last minute, you know, rather like my daughter getting ready for a party, that there isn't time, even at the speed of light, for the person here to know that he's changed his mind. Do these experiments still work? And within the past few months, there have been results published on new experiments that people have done to test that very question. And I'm going to show you another one. Some of us were looking earlier at today. This was in the April issue of Nature. And the title of the paper was An Experimental Test of Non-Local Realism. And it's one of these experiments where you have a laser and you have a crystal here that creates two entangled photons. And then you measure, Alice measures some here and Bob measures them there, and you can change the polarizer here and the basis in which you're measuring the angle of the polarization of the photons. And that's equivalent in the house analogy to changing which window you're going to look at and see whether it's open or shut. And they were testing here. Well, you can see these are the correlations. This you can't read it, but it's NLHV, non-local hidden variables. So here they're testing the experimental data against a non-local hidden variable theory. Here they're testing it against another hidden variable theory that's a set of theories that have been developed by the Nobel Prize winner Tony Leggett. And in both cases, what the hidden variable theories would show are shown by the dotted lines, and the curved line shows what quantum mechanics would predict, and the dots are the experimental data. And you can see that the dots here comply with the experimental data, and at least over some of the range give you correlations that go beyond the hidden variable theory. Actually, the new lot of stuff that Tony Leggett's producing is much worse fit to the data. So these experiments are completely consistent with the predictions of the quantum mechanics that was developed in the 1920s. Yeah.
Sorry, so I thought, let's say, some non-local hidden variable theories would give you exactly the same Bell correlations or correlations.
They do if you do the experiment badly. So how can I illustrate that?
Maybe you can correct myself. I thought Bohm theory gave you exactly the same EPR correlations. Or am I should call just experts on this, but
So this is, presumably this isn't Bohm's theory that they're ruling out, I suppose.
because Bohm's theory, I think, pretty sure
Bohm's theory works.
Bohm's theory gives you all the same predictions.
Okay, they're ruling out certain classes.
Classes of, yeah.
Okay, of
But-
non-local hidden variable theories.
Not Bohm.
All right.
Yeah.
No, not Bohm. I think Bohm's a sort of conjuring trick that says my car is powered by little green men. But they're specially trained so that whenever you open the bonnet to have a look, they run away before you can see that they're not there.
Not saying that's any stranger than this.
Okay. And this is a paper by serious people like Anton Zeilinger is one of the authors, published in a serious journal. Look at the claims that they're making. Okay? One could consider the breakdown of other assumptions that are implicit in our reasoning. These include Aristotelian logic, counterfactual definiteness, absence of actions into the past, or a world that's not completely deterministic. So they're making strong claims to this. I don't want to discuss that more now, though we may want to later on, except to say that, first of all, this is still a topic of active investigation, and second, that all the experiments that have been done on small numbers of particles, in this case 2, are consistent with quantum mechanics. And what this and other thinking has led to well, it has prompted an important insight. And the insight that these kinds of experiments and this kind of theory has prompted is the insight that information is physical. And that, at least for the field that I'm in, was most definitively set out in a paper in 1985 that many people regard as the manifesto for quantum computing. Oh, I'm sorry, I did want to say one thing, because it isn't in my slides here, on realism. We'll find ourselves talking a bit about realism, and I think, to go back to this one, that one of the things that we would find if we looked into it carefully is that they are using a definition of realism which is much more restricted than the kind of way we've been talking about realism today. And so there's a real question as to what you mean by realism. By realism, they mean a sort of almost deterministic outcome of any observation that you make on any quantum system. I think we've been today thinking in terms of a definition of realism that's a bit different from that, and I think probably more helpful. And I just put a slide here it was prompted by, there was a Bishop Berkeley in the 18th century, and he had theorized that all individuals, that all that you can know about an object or event is your perception of it. And he went further than that and said that this perception is one that's been placed in the mind of the observer by God. And this prompted a wag later, a century later, Ronald Knox, to pen this very donnish limerick. There was a young man who said, God must think it exceedingly odd if he finds that this tree continues to be when there's no one about in the quad to observe it. To which some other wag can reply, "Dear sir, your astonishment's odd. I'm always about in the quad. And that's why this tree will continue to be, since observed by yours faithfully, God." So there's realism for you in one side. On to quantum computing. David Deutsch was thinking about the Turing model of computing. The Turing model of computing was developed, I suppose, in the 1930s. Alan Turing was a fellow of King's College. The work that he did had terrific practical implications in the development of the bombs at Bletchley Park for breaking the German codes in the Second World War. Around about that time, the new insight about information had been that information is mathematical. And every time you use the internet or use your mobile phone, you're using technology developed by engineers who've grown up with Shannon's theory of information, and information down noisy channels. And what Shannon found was the equations looked indistinguishable from the equations for statistical mechanics that had been developed in the 19th century. And that's why information has borrowed terms from thermodynamics like entropy of information and so on. David Deutsch went further, and he said information is not just mathematical, it's physical. And he picked up on the work that Turing, and in the same year Church had done. This was work that had been done in 1936. And Turing said this, that every function which would naturally be regarded as computable can be computed by the universal Turing machine. And the universal Turing machine has been immensely influential in the development of computer science. But David Deutsch said, well, hang on a bit, this is really rather sloppy use of language. What does naturally regarded be? Can't we be a bit more precise than that and sharpen it up? And so he developed his physical version of the Church-Turing principle, which was that every finitely realizable physical system can be perfectly simulated by a universal model computing machine operating by finite means. And it's this insight that opened the whole world of quantum computing, together with some others as well. And the key point was that he wanted to, that his definition used objective concepts, and concepts that are already being tried and tested in, well, he says measurement theory there, but measurement theory in practice, one would say.
Does this mean that if you would normally expect to sum an infinite series to work something out, he's saying that you could instead use a finite series?
That might be a consequence of it, and we'll come to that, but he was more saying that there's a one-to-one correspondence between what you can do on a computer and the way the physical world is. That was the important point. So now I want to spell out some of the implications of that for you. And the first one is this, that we can have an operation that's like a square root of naught. So, you know, you can have a not operation. So, not true is false, all right? And you can have a not operation. So, not true is true again. Partly what we were hearing about earlier on today. You know, the linguistics lecturer who was explaining that in some languages, a double negative makes a positive. So that's true in English. You know, if my name is not Andrew, then it is Andrew. And there are some languages in which a double negative is a reinforced negative. That's true in Greek. But he said there's no language in which a double positive makes a negative. Some wag at the back of the lecture said, yeah. Anyway, in classical logic, you can't have an operation which, if you do it twice, gives you a not. But in quantum logic, you can. So there's the classical one. Okay, this is a not operation. Is everyone happy with this much matrix mathematics in a lecture at this level? So there was, it was, you know, if the top bit of the vector is whether it's true and the bottom bit is whether it's false, then 1 naught means it's completely true, and 0 1 means it's completely false. Okay. Now, in quantum logic, we can have a square root of naught. And there's my square root of naught operator. And look what happens. Okay, if I operate that on a 1, 0 vector, I get a 1, 1 vector with a 1 over root 2 to normalize it. If I do it again, then I get my not operation. So you see I've done this operator twice, and I've got a not operation. If you want to have fun, if you get bored with from now on, if you do it twice again, you'll get back to where you started with a minus sign in front, and that corresponds in the bang-bang experiment to having put the 180-degree phase shift on the thing. So this really does work experimentally. And the reason we're allowed to do this in quantum computing is because the 1-1 state physically exists. Okay, there's a physical reality to that vector that's represented as 1 over root 2, 1, 1. It's the quantum superposition state, and we've already seen that we can do experiments in the lab that use it, and for which it really works. And I can whiz through the next slide, which is about entanglement, because we've already talked about it, because entanglement makes something even more exciting possible. So let me just try to give you the notation, because it'll be useful for what happens. I'm going to start using the jargon qubit. A qubit is a quantum bit, which can be a 0 or a 1, or anywhere in between on the surface of the globe. And I can write it as a vector like that, where A and B are complex valued coefficients, because there's a phase between them that corresponds to the longitude on the globe. And of course it's A squared plus B squared, it's got to add up to 1. And I'm going to write a shorthand where the left hand, the first digit corresponds to the left hand qubit, and the second digit is the right qubit. And I can write a product state, which is the state with both the left qubit and the right qubit in it, by multiplying them together. And so if I take that and multiply it by that, I get this expression, and I can rewrite it in my shorthand. So these two are exactly the same, they're just written out differently. Now, if I have a state that looks like this, it's called an entangled state, and it cannot be written as a product state like that. So there are no values of A, B, C, and D that would enable me to write this in that form. It can't be done. And you can think that that corresponds in terms of the Windows metaphor, that if I measure on the right qubit and I find it's a 1, then for this particular state I must find that that correlates with the left-hand one being found to be a 1 as well, even if the measurements are done closer to each other than light could travel, signal could travel at the speed of light. So that's an entangled state, sometimes known as a Bell state, because it's the kind of state that you would use in an evaluation of the Bell inequalities. Now, this enables us to do another logic operation that you could not do in classical logic, and it's the square root of a swap. So you know what a swap is. I've got one state here and one state there, and a swap would be just that I swap them around. You could imagine doing that between memory locations in a classical computer. Quantum logic allows me to do a square root of swap. So here's my classical swap operation. Okay. Now I'm going to do a square root of swap operation. And my square root of swap is halfway to my classical swap operation. And you can see what it's resulted in. It's resulted in an entangled state. It's slightly different from the one that I showed on the last slide. It's another of the Bell states. And again, I'm allowed to do this in quantum logic because an entangled state really exists. It has a physical reality, and I've shown you already some experimental data on an entangled state. So the insight that information is physical opens up new possibilities in logic. And I'm not just making this up. I mean, this is now a matter of history, that the paper that David Deutsch wrote and others that went with it have opened up this vast field of research. I suppose it's worth saying just in parenthesis that this is not something that's restricted to the physical sciences or even the quantum sciences. And some of you may know Malcolm Jeeves, who's had produced some accounts of comparable insights in the field of psychology, that things that one would previously have thought of as abstract nouns, like sort of behavior and personality and so on, have their physical embodiment too. One famous case was the 19th century case of a railway worker called Phineas Gage, who had in an explosives accident, had a bar that I think went through his cheek and through his head. I think it blinded him in one eye. But otherwise, he seemed physically to recover within about 24 hours, and it was quite an extraordinary case. But this man, who had been a good citizen and a good father, became a sort of ne'er-do-well, and underwent an abrupt, what should we call it, personality change that correlated with the physical change to his brain. In one of the issues of Dennis's journal, Science and Christian Belief, Malcolm gives the story of the Virginia school teacher who started to sort of indulge in pornography on the web, was eventually prosecuted for molesting his stepdaughter. As the treatment was beginning, he got this terrible series of headaches, which was diagnosed as being due to a rather big brain tumor. The brain tumor was cut out, and the lewd behavior stopped, and gradually reasserted itself over the next year when they discovered that they hadn't completely removed the tumor, so a second operation was performed, and then the lewd behavior stopped again. Now, you see where this is going. Supposing that you found me looking at porn on the web, or molesting a teenage girl or something, you'd say, "Stop it, Andrew. Don't do that. Stop it. You treat me as a responsible person, who ought to behave properly, and you'd be right to do so." And yet, what this is showing is that the mapping of that kind of language onto the physical structure of the brain is something that we need to take into account. And there's a lot more experimental evidence coming up from functional magnetic resonance imaging and so on. What I want now to begin to introduce is the way that this may be relevant for our thinking about God's involvement in the physical world. And it may be that it's a topic we can pick up on in the discussion or in the panel after dinner. And up till now, what I've been telling you about is pretty well established science. I may have explained it well or badly, but I mean, insofar as I've explained it well, it would be agreed by most people in the field, I think. I want to move on to how that might, what shall I say, be a parable for the way that we think about God's involvement in the world, and something that I hope that we can draw out in the discussion is to what extent it is a helpful parable, and perhaps how strong a parable, and whether it goes beyond that. One of the early skeptics of quantum computing was an information scientist at IBM Labs in Yorktown Heights called Rolf Landau. He was a very distinguished scientist. In fact, it was interesting, at that time there were two. There was him and Wheeler, who were both industrial scientists working in an industrial laboratory, who would be world renowned for their academic and intellectual contributions, as well as their contributions to theory. And about 11 years after the paper by David Deutsch that I mentioned, Rolf Landauer wrote a paper on the physical nature of information. He'd been skeptical about quantum computing because he reckoned that decoherence would always kill it off. We've talked about the way that decoherence may stop the brain from ever using quantum entanglement. He reckoned that in any experimental system, decoherence would kill you, and you'd never be able to do practical quantum computing. What made him change his mind was the development of techniques of fault-tolerant error correction, whereby, provided you could get the decoherence time a few orders of magnitude longer than the gate operation time in a quantum computer, you would be able to go on correcting errors indefinitely. So you could run a quantum calculation forever using these fault-tolerant error correction schemes. In fact, the experiment that I showed you earlier from the Oxford laboratory showing entanglement was done in the laboratory of Andrew Steen, who was one of the people who invented fault-tolerant error correction. So in this paper called The Physical Nature of Information, which was published in 1996, Rolf Landau started it off by saying information is not a disembodied abstract entity, it's always tied to a physical representation. It's represented by an engraving on a stone tablet, a spin, a charge, a hole in a punched card, a mark on paper, or some other equivalent. And he then went on, having his skepticism having been overcome about quantum computing, to write a paper, most of which was about quantum computing. But then it ended up like this. Our scientific culture normally views the laws of physics as predating the actual physical universe. The laws are considered to be like a control program in a modern chemical plant. The plant is turned on after the program is installed. And at this point, I was wondering if Berry could tell us. Berry had been discussing with her class the nature of physical laws and their status. You probably didn't call them that. Tell us about what you found, Berry. Tell us loud enough so that everyone can hear.
Right, this is my PhD, and I've talked to lots of people about it, so I'm probably about to bore you all, but basically I was looking at how children and undergraduates who aren't necessarily studying science, but are studying all subjects, how they think about nature because of science. And what was striking was that, particularly when you talk to school students, they think that science came first. So, for example, and the laws are something that nature has to obey, so nature has to obey scientific laws. And one of the very telling things was when I asked children to talk about experimental error. And experimental error is the mistake your experiment makes when it doesn't get the answer in the textbook.
Many students certainly think that.
Well, Rolf Landau, in this paper, finished off by evaluating just the kind of thing that you found out in your PhD. And he actually was arguing against a sort of Platonic view that said that the mathematics is the ultimate reality to which the world that we observe in experiments then approximates. And he was arguing against that. But the way he did it was to quote the opening words of John's Gospel. In the beginning was the Word, and the Word was with God, and the Word was God. And he gives a little definition of the Greek word logos. Of course, John was the master of double entendre, and the term logos at that time had more than one meaning. It had this kind of meaning from the Greek world of philosophy, but of course it also had a meaning drawn from the Hebrew scriptures, where hadabar, the word of God, was something active. It was God acting in the world. And I'm sure John was very happy to draw in both of those meanings in talking about the word at the beginning. And of course later on you get this in verse 14, this extraordinary juxtaposition which is as forced in Greek as it would be if I translate it literally in English, and the word flesh became, because it bangs together two words that would not naturally belong together in Greek concepts or in Greek syntax for that matter. And so you can take the word, something that one could think of as being a sort of abstract idea since then, certainly related to information, and you have there right at the start of John's Gospel the physical embodiment of the Word. The Word became physical, flesh, meat. C.S. Lewis wrote that the central miracle asserted by Christians is the incarnation. I think I've often thought, and we've often talked today, as if the central miracle is the resurrection. And the central Christian festival, therefore, is Easter. And I understand why we say that. I understand the importance and the excitement and the joy of it. But the crucifixion and Easter are only possible with their full significance because you first had the miracle of Christmas. They say that God became man. Every other miracle Lewis wrote prepares for this, or exhibits this, or results from it. Well, there's a lot more that I could say, and I've got some specific workings out of that I could give either now or after dinner in the panel session. But what I'd really like to do is to stop at this point and have a sort of stop and think time together as to what you make of all this, where you think it might take us.
Thank you very much indeed, Andrew. We're going to have a time of questions and discussion, then leave a little bit of time before dinner. But we do have some time now, so over to you. Yes.
Is the bottom line of what you're just saying about information that you advocate an Aristotelian view of the universe rather than something more Platonic? In other words, abstract ideas go, all the ideas have to be embodied in something physical.
I've actually published on this topic in a place where you least expect it, and that was the letters to the editor of the independent newspaper. And it was prompted by a leaflet that I got with my car tax disc in the days when I got it for the DVLC. And it was an advertisement of seatbelts. And this leaflet, which I suppose had gone out to everybody who has a car in the United Kingdom, or a vehicle in the United Kingdom, under the heading, it was telling you to wear your seatbelts, or telling the people in the back, it said that when a car is involved in an accident at 70 miles an hour, the passenger is thrown forward with a force equal to the weight of an elephant. And it absolutely beggared belief to me that the combined scientific knowledge in DVLC should be at such a low level.
Could you just explain DVLC, Andrew, because not everyone will know what that is.
Something Vehicle Licensing Centre,
yeah,
Driver and Vehicle Licensing Centre.
Yeah.
That they could write such gobbledygook and circulate it to every vehicle owner in the United Kingdom. And so I wrote to the newspaper that sort of sentence might have been fine for people who believed in Aristotelian worldview, but Newton had made it untenable. So that's actually not quite what you were asking, was it? But I wanted to tell the story. So I don't actually know whether or not, I'll leave it to other philosophers I believe what I've just told you this evening, and I'll leave it to those more expert to say whether or not that's consistent with Aristotle or Plato.
Yes, do you want to go first before Art? So, yes.
I was thinking about this comment about this person who got a spear through his head or something.
Oh yeah.
And you have similar studies on split brain
Yeah.
patients and so on. But you have studies like from Jeffrey Schwartz also with patients will have obsessive compulsive disorder, and they have a tendency to something called neuroplasticity, that they can change their neural inner workings.
Yeah.
What's your take on that, and how do you?
I think it's such an interesting field of discussion that I'd love to save it for the panel after dinner, because there's a sense in which it was an aside on what I was mainly talking about. And so could we pick up that area in the panel discussion and perhaps focus the discussion now on the main things that I was talking about?
Okay, Art, yes.
So I just wanted to follow on Peter's question a little bit. So could you expand, when you were talking about the quantum states, you made the statement and this, I think I'll get it not quite right, but you basically said this state is real because we can make it. Right? Said something along those lines, which I think was linked to your point about information being embodied. but you're just putting together a state which. What did you mean by that? Why would this state not be real if we weren't able to create it?
Let's leave out the word real for the moment, because it's a very important word. But let me make a really robust statement and say that these are states that we can create in the laboratory in the sense that we can do measurements on them and get results that are entirely consistent with the quantum description that I was putting up in the matrix mathematics. That's what I mean. So therefore, one can imagine building a computer that depends on that kind of logic, and provided you can solve the technological issues, which are formidable, you can actually get it to run quantum programs that work on this kind of logic. You could not do that with CMOS, except in the limited sense that you can simulate a quantum system on CMOS.
Just to clarify, so it would be really surprising to me if, with all your technological, if you got the technological skill where you could make an isolated quantum system with two spins, that it wouldn't follow that quantum mechanics.
Yeah.
Right? That would be very surprising. So.
Fine.
So what is special about the fact, I'm just trying to tease out what you mean by information being embodied, or what did you mean by the special status of the fact that you could make these things? Besides the fact that, quantum mechanics is once again confirmed.
What the cash value of it is this, and I don't think that what I'm about to say would have been perceived without the process that I described. Well, as a matter of historical fact, it wasn't perceived without the process that I described. You can program your laptop to simulate perfectly a quantum system. So you could say, well, we'll take my laptop, all the clever things you've been talking about, quantum logic and so on, we'll program my laptop to simulate them. Fine, you could do that. So why bother with the quantum computer? As you try to increase the number of quantum bits that you're simulating on a classical computer, the amount of computing power you need scales exponentially. So for a big problem, it would rapidly become intractable. If you can exploit entanglement, superposition and entanglement, then every time you add one quantum bit, which I call a qubit, you double the computing power at your disposal. So supposing that we made something that people aspire to but haven't yet made, a 100 qubit quantum computer, and you said to me, Andrew, that's just not up to the job. I need something that's 1,000 times as powerful as that. I say, fine, we'll add 10 more qubits. So instead of it being a 100 qubit quantum computer, it's now 110 bits, and it's now 1,000 times more powerful. And you say, that's not enough. I want it to be 1 billion times more powerful. I say, well, that's all right, just another 20 qubits on top of that, 130. And so you get this amazing scaling of the power of the thing that scales exponentially with the linear increase in the number of qubits. That cannot be mimicked in a classical computer. And that's why if you could build these quantum computers, people would get terribly excited.
Exploiting the parallelism. The quantum parallelism.
That enables you to exploit the exponential. And as any of you know that story of the Chinese emperor who agreed to a deal whereby he put 1 grain of rice on the first square of a chessboard and 2 on the second, all up to the 64. And it turned out to be more rice than China would ever produce in the rest of the evolution of the universe. That's the power of the exponential.
But I'm still trying to tease out this, what did you mean? So I understand why quantum computers are exciting because of this exponential growth. And are you, maybe, see if I understood, are you trying to say precisely because you had an exponential growth of the computing power with size, therefore that information is somehow embodied, has to be embodied in those kinds of systems. Is that what you're saying? I'm just wondering.
It
I'm trying
actually,
to get,
it actually came the other way round, okay? That all computers were built on Boolean logic, okay? Classical Boolean logic. That's how this works. And as it happens, they're built on irreversible Boolean logic. That's not necessary. You could build a reversible classical computer, but Intel don't bother. There had been other inklings of what you could do with a quantum computer. Feynman had ideas about it. But what David Deutsch saw was that if you took what had become the definitive model for all computing science, namely the Turing machine, and you improved the accuracy of the way that you talk about what a Turing machine can do, then you, in order to get that improvement in accuracy, you need to talk about the physical realization and not, I can't remember what the phrase was, you know, things that you could imagine. And when you come to talk about the physical realization, the physical description you should be thinking of is a quantum description. So that was his thought process. And it was that that then led to the ideas of quantum logic that you could implement if you built a quantum computer. And they're in that 1985 paper by him.
Okay. Anybody else want to come in at this stage, or? I think what we might do actually is I think we need a bit of a break before dinner. Dinner starts at 7 o'clock. So I think we will break now because we do have the panel discussion later on. And just a couple of practical things before thanking John again. So once you get to dinner, you'll suddenly find it's 8:30 in time for the panel and you haven't written down your questions. So what I would suggest you do is to write down your questions on the way out and put them straight in the box. And that also gives our chairman a little bit of time to go through in 5 minutes and pick out the questions before the panel starts at 8:30, which will be back here.
And on the panel, we'll also have tomorrow's speakers. I don't think Bob will be here. There will he? Not Bob White, but Don and Peter. So if you have any kind of questions on multiverses or cosmology, I mean, obviously we'll have sessions with them tomorrow. But
and I would be very happy to take questions on the practical implications for theology of the kind of things I've been trying to present here.
Yeah, I think that would be very good to kind of tackle that, ask questions along those lines. So.
Good, yeah, so that would be brilliant. And we'll be back here then, dinner's at 7 o'clock in the dining hall, and we'll be back here at 8:30. And we'd just really like to thank Andrew again for a great talk, so thank you very much.